Okay, so today's webinar is about dam breaks and tailings dams. This is a very interesting and important topic for many reasons. And in Hadronia, we have taken a lot of interest in making our tools useful for this type of assessments. So today's webinar is about how we can provide you with the tools that you need for making these evaluations in your projects. Now, there are several challenges in simulating two-dimensional dam break flooding. First, the issue of the high velocities and regime changes. So in dam breaks, they usually occur in steep areas where the flow is complex, the terrain is very abrupt in many instances, and you have changes in the flow regime. You have supercritical flow in some reaches and subcritical flows and changes that occur and also vary in time. So this is a big challenge in doing a two-dimensional modeling for this type of flows. Also, the boundaries are totally irregular. Its flow is usually unconfined in the lower reaches of the valley, and you cannot specify a specific boundary, and even the internal boundaries are irregular. On top of that, if you're dealing with tailings dams, and tailings dams, for those of you new to this topic, is a dam that or a reservoir of residuals of mines. So it usually contains toxic fluids, but sometimes they are not toxic, but they are always viscous fluids. And often the fluids that you need to deal with are non-Newtonian in nature. And I will talk about a little bit about this later and what is important in modeling tailings dams. Let me give you a brief video here that I took from a BBC News, but it shows you the devastation that a tailings dam break can generate. And this is from a very recent event that occurred in Minas Gerais in Brazil. It's very unique for many reasons. Now, let me show it to you. It just takes a few, less than a minute. And I will make some comments after that. If I can show the video, of course. Okay, so this is the thing. There are several important issues that occurred in this particular dam. There were not one dam, but two dams, and the first one failed, still for no reasons. There was a second dam downstream that failed after caused by the effect of the first failure. And then all this fluid that is an iron ore from an iron mine flowed downstream for 60 kilometers and affected 5 different towns. And this occurred in a very short time period, so the people didn't have enough time to be warned. So it's extremely important to be able to assess the risk of dam breaks, in particular tailings dams. And the model that you need to use to model this type of events need to have certain requirements. Now, which requirement do you need in a 2D model that you want to use for a dam break study? Well, if it's a water dam break or a dam break from a water dam, it needs to be capable of dealing with complex terrain and urban areas that often are downstream of the dam. It needs to handle abrupt regime changes, supercritical and subcritical regimes. And in the case of tailing dam breaks, it needs to have rheological formulations that would be able to realistically capture the properties of the fluid. Now, there are many different fluids based on the mine, the residuals that you may have there. And there are specific rheological formulations that better adapt to some fluids. The take-home message here is that there is not a single formulation for all fluids. So it's convenient to have different formulations that would be better adapted to your fluids. And in all cases, you need to have a model that accurately predict the depth and velocities, but not also the depth and velocities, but also the frontal wave arrival. How accurate is the model in predicting when the frontal wave is arriving? Because that's what will allow you in advance to give the warning to the population. So and this is critical for saving lives. If you can predict accurately how fast a given dam break flooding will arrive to the different locations, then you will be able to save lives, and that's what matters in the first place. Now, I will talk today about the RiverFlow2D model, obviously, because RiverFlow2D models, for those of you who are not familiar with it, is a model that is developed and distributed by Hydronia. And I will also talk about other models in regards to how they compare with RiverFlow2D today, briefly. But mainly, the RiverFlow2D model is a combined hydrologic and hydraulic model. So it does not only the routing of the hydrograph, but also it can do simultaneously rainfall and infiltration. It's based on a flexible, non-structured mesh that can be adapted to any geometry and terrain. It uses a robust dry-wet bed algorithm. The solution method that we use is the finite volume, is one finite volume numerical method that can handle supercritical and subcritical regimes. It has been extensively validated. It also does sediment transport with erosion and deposition, pollutant transport, mud and debris flows, which is the module that we use for tailing dams. It can do also hydraulic structures in 2D, bridges, gates, weirs, culverts, etc. It works in English or metric units. It's completely integrated with SMS GUI. I will talk about this in the example that I'm doing at the end. And it also has a GPU module or GPU license version that runs much faster in the GPU environment. Now, all this is possible because we have a collaboration agreement with the University of Zaragoza. And this is very, very strong collaboration that allows you to be developing new features all the time for the model. And one of the features that we have developed is the mud and debris flow module for tailing dams. Now, we always talk about flexible mesh, and many people understand this, but what is actually a flexible mesh? In the framework of the RiverFlow2D model, the flexible mesh is just the mesh forms of triangular cells or elements that can be adapted to any geometry or terrain. So if you have buildings or houses, as you have here in this image, the mesh can be generated around the buildings here so that you can capture the obstacles that can affect the flow. But more importantly, the fundamental cell, which is the triangle, that mesh generation engine can provide you all the tools that you need to generate the mesh in any environment, can have a velocity and depth, and the velocity can vary in any direction. So there is no restriction to the direction that the velocity can have within the cell. So this makes it a full 2D model in the context of RiverFlow2D, because there are some models that restrict the directions that the velocity can have inside the cell. Now, this allows you to create very complex simulations and very comprehensive simulations of the velocity and flow fields that can occur within your mesh. And that's very useful to analyze risk assessment in the context of also of the dam break flooding. Now, the flow equations that we use are the shallow water equations in conservation form, and that allows us to conserve volume and momentum very accurately, as we will see. Now, there are two terms in the equations that I want to focus on in here. This the stress terms that are important when dealing with the non-Newtonian flow equations that we use for the tailings dams and dam breaks of tailings dams. Now, as you know, in the Newtonian fluids, water is a Newtonian fluid. There is a constant relationship between the shear rate and the shear stress, and it's constant in time and space because it's proportional only to the viscosity, which is not changing. This makes the computation relatively simple to implement. Now, there are many fluids that behave like non-Newtonian fluids, and what this means is that the viscosity is no longer in general constant. It can vary based on the shear rate as the Bingham fluids, but also they can, even though they may be constant, they show the fluids show that they have a yield stress. And what this means is that the yield stress is a stress that needs to be overcome to move the fluid. So there are some stresses that make the fluid to stop. So if the velocity or the forces acting on the fluid are below a certain value, the fluid will stop based on the yield stress it has. And this is typical, very common in tailings dams fluids. Also in mud and debris flows events, but in non-natural events like the one I showed you before, it's very, very common. Now, there are other terms in the equations that are very important as well. And all of this are taken into account in the RiverFlow2D model. Now, there are two types of equations that we can deal with. Some of them relate to the typical Bingham type formulations. There are some formulations that are more common in granular flow when the fluids are drier, has less moisture content, And we also take into account this in the rheological formulations that are included in the RiverFlow2D model. So in the model, we provide 8 different formulations that you can select from the simple or relatively simple turbulent Manning's based on Manning's N equation to the Bingham fluids and combinations of them that includes also granular flow. So if you have a purely granular flow with no water content, you can also use the RiverFlow2D MD module to simulate that type of events. Now, there are several numerical properties that are important for any flood analysis, but in particular for dam breaks. And one of them is that RiverFlow2D is accurate regardless of the flow regime. So it doesn't matter how high the fruit number is, you get the same level of accuracy for the velocity and depth of flow, and also the frontal wave advance. The volume and mass conservation error that the model provides is always very low. We call it 0. It's not exactly 0, but it's always almost 0. It's 10 to the minus 14th percent. So you can imagine that number, what it is. But it's 0 when you consider the numerical accuracy that you get, or numerical precision that you get with the computer. So it's in the order of 0 for that all practical purposes. Now, other very important feature is that the model is not sensitive to the time step for the current number that we recommend that are lower than 1, and typically between 0.5 and 1. The model is insensitive to what the current number provides. So you don't need to be calibrating with a numerical factor your results, because the numerical results are insensitive to the current condition. There are many tests that the model has gone through that show that the model is always stable, consistent, and convergent on the complete range of realistic river inflow situations. Now, there are other features of the model that include hydraulic components, internal rating tables, sources and sinks, bridges, gates, culverts, weirs, and these can all be used. They can be used together with a dam break simulation. So if you want to model a dam break, but in the floodplain or in the river you have structures that need to be accounted for, they can be used in the model as well. Now, the model, as I said, has gone through a large set of benchmark tests, but I will show you today some of them only that are related to dam breaks. And there is a simple dam break, relatively simple dam break experiment. This is an experiment that was done in a flume, and measurements were taken at this gauge location. So there is an initial dam here in the flume. It's a horizontal surface with an obstacle here, and suddenly this dam, this gate is removed or open, and then the flow gets into this downstream area that is initially dry. So we have measurements along these gates. I'm showing you today only one of them, this G4, but you see here the points indicate the data, and the line indicate the RiverFlow2D results, and it's very close, the agreement that you get with the model. Other tests that have been done include, this is a cylindrical column collapse. It's an initially cylindrical surface here of a fluid, and then it's removed at time 0, and then we compare how this surface moves in time. And what you see here is the comparison of the model with the measurements. It's very close. And sometimes we get questions, well, what's better, using a grid model or a mesh model? Well, there are many tests that show that, particularly for granular flows and for non-Newtonian fluids, the structure mesh, the grid mesh, tends to generate some artifacts in the model based on the directions of the mesh. And you see here the same cylindrical collapse sample here. You see here that the surface shows this strange patterns that should not be observed in reality. When you look at the results of an unstructured flexible mesh, as the one that you can have in RiverFlow2D, you see that the results are much more symmetrical as you would expect. The model has been applied to many practical problems and real events as well. This is the applications to Rut Creek Mudflow event that occurred in Utah in 1983. And the reason that this was applied for this is that there is a good database of what occurred there, the topography, the extent of the flow, the velocities, and so forth. And this is the inflow location. It's a little town here, but very viscous fluid entered from upstream on the creek. And you can see here the extent of the affected area. And this is the final simulation area, the depth of flow and the velocities. And the velocities that were observed with respect to what the model predicted was pretty close. Now, let me briefly talk to you about the how the model compares with other models. And we have done an extensive set of tests. We had a webinar. If you want more details, you can watch a webinar we gave last month about this topic. But I will summarize what we had in a test that is related to dam break. But also I will extend the results because we have new results of different tests we have done in this same benchmark. Now, this is test 5 of the UK benchmark. The UK Ministry of Environment has a set of benchmarks on which you have open access to the data, and you can model and compare with other models. And this particular test, it checks the model capability to simulate major flood inundation and predict flood hazard arising from a dam failure. And it allows you to check the peak velocities, water surface elevation, travel times, etc. Now, travel times is very important, as I said before, because that's what helped you alert people. So the test is designed to simulate a floodway propagation down a river valley following a failure of a dam. This is the inflow hydrograph that is imposed upstream here. There is a valley going downstream, and then a confluence here. And there are location points. These numbers indicates observation points where the model is to be compared. Now, we use 3 models. We use RiverFlow2D, Gerais beta version, the latest that has been made available, and SRH2D, which is a model of the US Bureau of Reclamation. By the way, these 2 models are free, and normally SRH2D uses the same SMS interface as RiverFlow2D. Gerais2D is made available for free. That's not the case of RiverFlow2D, that is a proprietary model. Now, when we started the comparison because we wanted actually to focus on performance, because RiverFlow2D is known to be a very fast model. and I want to know how faster was than other models. And that's a question we often get from our potential clients and people who get interested in the model. How much faster is RiverFlow2D than other models? So we started comparing times. Then during the test, we came up with some weird results, and the results are shown here. These are velocities and water level depth at different locations based on the requirement of the benchmark that requires to use around 7,000 cells. In this case is 7,500. That's not exactly the same for all models, but almost the same. But the weird thing here is that in the case of Gerais, the results change significantly in some locations based on the time step that you select. So if you select here a time step of 10 seconds, the results are more or less close to what you get with RiverFlow2D and SRH2D, which is at the same time closer to what you can see in other models like Mike21 and 2Flow. But Gerais2D is significantly different, especially with lower time steps. And if you see here, this is the velocity versus time at location 5. It gives us a very big difference in the travel time or the arrival time of the wave. So that's, and here too, you can see this, the levels are very different here. So this was communicated to the developers of the RAS models, and they're aware of this, and they indicated that you need to also to make it converge to use very small cells, and that's but the thing is that this is the number of cells that the benchmark requires. Now, in terms of volume conservation, RiverFlow2D is always very volume conservative, as you can see here. Gerais2D tends to vary depending on the time step you select. The time step sensitivity of RiverFlow2D, as you can see here, you see two results of one, CFL current number 1, current number 0.5 is exactly the same results for all points. Now, time step sensitivity, as you can see here, the results vary significantly for Gerais2D, as also shown before. Now, when we improve the mesh, the runtimes also change because obviously we use more cells. For the 7,000 cell mesh or that order, the results show that RiverFlow2D GPU version is between 13 and 57 times faster than RAS2D, depending on the time step you select, and also is 99 faster than SRH2D, also depending on the time step you select for SRH2D. Then we did 7,000 cell mesh, and these are new results. And we obtained better results, more comparable between the models in accuracy. But the time steps are optimized in these two models. RiverFlow2D doesn't require optimizing time step because it does that automatically. In this case, it turned out that RiverFlow2D GPU was 16 times faster than SRH2D and 23 times faster than RAS2D. Then we did 10 times more cells, so 700,000 cells. In this case, we ran only with Gerais2D. SRH2D took too long, and we haven't finished the run yet. But it takes, in this case, RiverFlow2D is about 24 times faster than RAS2D. But look at the times. It takes 25 hours to run this case in RAS2D and 1 hour in RiverFlow2D. This has a big impact on your modeling process because Instead of waiting 1 day for the results, you can have results in just an hour or minutes. Now, let me show you some applications. We'll show you a couple of them. One of them is related to a tailings dam risk assessment. And this is in Mexico. And we were not allowed to provide the name of the dam, but this is a tailings dam in Mexico. But the important thing here is that this is the initial condition. So you have elevations of the fluid here in the dam. This is the dam. It has a height of 90 meters. And it's a huge dam. It's about, I think it's 11 million cubic meter that is accumulated upstream of the dam. We did two cases because there was a hypothesis of the risk analysis that the fluid may be very dry because it has been staying there for a long time, and most of the liquids have percolated and gone out of the solid material. So we assume totally dry material using the granular flow formulation that is available in RiverFlow2D with a friction angle of 38 degrees and density, this density, and these are measured actually because they were provided by the mine company. And we did also a different case assuming much wetter material with the Bingham formulation that is applicable to more fluid materials with this yield stress, this viscosity, and this density. Now, I'm showing you only here the final run out or the total view after the fluid had stopped. In this case, in case A with the granular material, the fluid stopped 1 hour after the dam break. And you see here that this is the original dam. The fluid went downstream about 500 meters and then stopped. So the danger or the hazard zone based on a pure granular material is very minimal, and it wouldn't affect anybody here because this is a very unpopulated area. Now, in case B, when we analyze the case of much wetter material, the flux 10 after 1 hour is about 14 kilometers, and it does affect a town downstream. So there is a big difference in which rheological material formulation you use for the specific material you have. And you see here, this yellow line indicates the flooded area using the granular flow formulation. So the point here is that it is convenient to have different rheological formulations available so that you can adapt it to realistically predict your run out distance based on the actual characteristics of your fluid, of the fluid on the dam. The second example I want to show you is very recent, and it was performed by Asier Blacasta, which is a long collaborator of our modeling development team at the University of Zaragoza. And this is from a paper that has been submitted to the Journal of Hydraulic Research. And it shows a dam breach and dam break flooding downstream, but it is modeling the overtopping of the dam with sediment transfer formulation using GPU. Now, the GPU version that we have commercially available is only provided in CPU hardware. So we don't have a version for the GPU sediment transport model, but we do provide the services for those of you who would be interested. If you have a license for the sediment transport model, you can send us the file. We provide the servers to make the run in high performance GPU hardware. And it's a very cost effective way to access these very fast simulations that you can do for, typically you need to do many runs, and doing this in the GPU environment saves you a lot of time and resources. So let me explain to you what you will see here. This is the Toast Dam. This is a dam that actually failed in Spain in the 80s. And what is being modeled here is the failure of the dam. All the dam is here. This is downstream. This is the reservoir. And you will see here the velocities. And you will see here how the dam is actually being eroded during the computation. So let me start simulation here. So you see here the velocities and how the dam is eroded, and you see here the dam erosion, and the dam material is actually being deposited downstream. Let me put it one more time so you can have a chance to look at you see how the velocities are being propagated upstream, but the very high velocities are in the dam location. Now, RiverFlow2D sediment transfer model it can be run in fully coupled mode. So every time step, it computes the hydrodynamics and also the erosion and or deposition areas. So it's very good for very rapid events such as the one you have seen here. So this has been submitted. It's under revision on Journal of Hydraulic Research, and probably you will see it very soon published there. Now, we have some time available, and I want to show you how to set up a full dam break simulation using SMS and RiverFlow2D. Because it's very nice to look at animations and things like that, and normally what you see out there, very nice animation, but you don't know what is beyond or behind that, or how long does it take to generate that kind of results in the model. And I want to show you how to set up a dam break simulation from scratch. Now, those of you who have the model or you have the trial version, you can also do most of what I'm going to do today here. But I want you to have a sense of the different steps that are required to set up a model like this. I'm using the Malpasset dam break. Malpasset is a dam that failed in the 50s in France, and it's very well documented, and is used worldwide to test models as well, because they are measurements of what happened downstream. So let me turn to SMS. So this is the SMS interface, and what I'm going to do is to load the RiverFlow2D template first. So I'm using the example projects that come with the version, with the model, with even the trial version comes with this this data. So what I have here, well, let me first, before loading the data, let me load the template. And I will also load the set of coverage. Some of them I'm going to be using. I'm going to be using initial conditions for the reservoir initial elevations. And I will also use the mesh map data coverage, where I will put the boundary of the domain. So let me now, I will import shapefile that includes the domain outline. This is the area that I want to cover. This is the reservoir area. This is the area where the dam was located. So all of this is the reservoir. And this is downstream, the valley, and the bottom extreme here is the the sea downstream. This is Mediterranean Sea downstream. Now I will also load another shapefile I have with the initial water surface elevations. This is here. So if you look at this is the initial elevations here. I will use this for setting the reservoir elevation, and downstream will be dry. Now I want to import also the bed elevations, and I will use the import wizard. So these are the bed elevations. Let me counter or use colors to show the values. These are the lower points are red in this color scheme, and this is the reservoir here. Okay, so what I'll do here is I will transfer first the domain outline to the mesh map coverage here. So I will use the map shapes to feature objects. So now I have here, this is the contours. You can also draw the polygon, but it's easier to have a shapefile. I had it already. So I have the whole contour of the mesh I want to develop. Now the second thing I want is to transfer the initial water elevation shapefile to the initial condition file. And I will use the shapes to feature object command as well. So I will transfer this to the initial condition file or coverage. And I will have here the elevation of the polygon upstream is 100 meters. You can change that, but that was the elevation of the reservoir at the moment of the dam break. So I now have an initial condition coverage here that has the polygons. So I will convert the nodes, the vertices to nodes. That's a requirement. And I will use the build polygons so that just to make sure that this attribute is set to 100 meters. So this is the elevation of the reservoir. And downstream, the polygon has an elevation of minus 9998. So it means it's dry. So there is no water here. And there is 100 meters of water upstream here. Okay, so in the mesh coverage here, I will want to have a finer mesh. So what I'll do is I will redistribute the vertices on the contour to 100 meters. And this will drive the size of the mesh I will get here. And I will build the polygons and indicate here, I will link the bathymetry to the scatter set corresponding to the bed elevations that I imported. Okay, so I think I have all I need. I will save this whole file. And what I need to do is just generate the mesh. Oh, I'm missing something, sorry. I need a boundary condition downstream. Let me leave it this way. I will leave it close, so the water will get to this boundary and stop there. But there is a way to define the downstream boundary condition as open. But just for the sake of saving a little time, I will leave it that way. So let me generate the mesh using the feature object map to 2D mesh command. So now I have the mesh here. Let me color the elements by contour, depending on the elevation. So those are the elevations that have been assigned to the elements. So remember, this is the location of the dam here. Okay, so the only thing we need to do is to indicate that we are using initial conditions is not a dry bed, is defined by the polygons that we selected. And I will run the model. So the model should start running, and as you see here, there is a little window that shows you the water depth, and it took 3 seconds just to compute the whole dam break of Malpasset dam. Now, obviously, this is with 100 meter elements. If you want to use smaller elements, that will take longer, but it's pretty fast in general. And this is not the GPU version. This is just the CPU version. The RiverFlow2D is really fast model. So what I can do now is show you how to import the results. And it can be imported in several different ways, but one of them is just to look at these are the depth, for example, at different times. And you can see how this changes in time. And you can turn to the 3D view very easily and look at the results in 3D. So it took us, I don't know, 10 minutes to set up a full dam break simulation for RiverFlow2D. One of the good things of RiverFlow2D is that it doesn't need any adjustment parameters, you know, this ad hoc type of weird parameter or factor there that you need to tweak to make it work. There are not such a things in RiverFlow2D. Everything is controlled automatically, and the model performs very smoothly, and also ensuring that you have full volume conservation all the time, which is extremely important for dam break analysis. And travel times are also very accurate. Okay, so let me go back to the presentation. Now, the questions many people ask and ask us actually is which model to use, you know, and why using your model. Now, the questions we think you should ask yourself is if your model, if the model you're selecting has been verified and validated, and if it has, you need to look at how it was validated. What, you know, look at their tests, look at how it was published, it was, you know, how it performs with respect to other models. Can your model handle in-channel flow in 2D, full 2D? That's very important for dam break in 2D. Is the model fast enough? Now, what is fast enough? And if you have a model that takes 24 hours to give you a result, or if you have a model that takes exactly the same mesh, it does it in 1 hour, well, that will save you a lot of time in your project. Now, in case of tailing dams, you have to think on the rheological model that is available, if it's right for all fluids. Now, we get this question all the time: why RiverFlow2D? Well, this is what we think, why we recommend people using RiverFlow2D. Well, it has more features than many other models. It can be used not only for flood simulation, which does it very well, very accurately, very fast, but it can be used also for erosion deposition studies, water quality evaluations, mud and debris flows, depending on the module that you want to use. You have 3 different modules. It is a very powerful model. It can do very large reaches or smaller reaches at very high resolution. As an instance, we are doing with NOAA, the Red River of the North. It's been an ongoing project for more than a year. It's a very nice and big project. It's 670 kilometers, 420 river miles, and it takes less than half an hour, or around half an hour, to run in the coarse mesh a 60-day hydrograph. So this is a very unique timing for a 2D model in this type of reaches. Now the model is very accurate. It's been validated with hundreds of tests, and it always generates zero volume conservation error, always. It's very fast, as I said before. It can be very fast, and this is a case of this particular timing is for the UK benchmarks. Dam break analysis at 6B is one of the UK benchmarks. In this particular benchmark, RiverFlow2D GPU is between 12 and 40 times faster than RAS2D and 200 times faster than SRH2D. As you have seen, it's very easy to use. It's fully integrated with Aquaveo SMS that provides all the tools to enter data, generate the mesh, visualize results, make animations. And it's also very affordable. It is lower in price than other competing 2D models, and if we believe is more cost effective even than free models, because the overall process of modeling is not only, the cost involved is not only price, it's the time you spend using the model, tweaking the model, making it work, waiting for runs, and so forth. So when you account for the whole modeling process, RiverFlow2D turns out to be much more cost effective than even free models. We provide comprehensive technical support and training to all users worldwide. And the way we license, we have single user network licenses. We make agreements with government agencies for site licenses. For academic institutions, we provide 50% discount. And this is very convenient because it provides 2 permanent licenses for professors and unlimited license for students. And we have a special discount offer that will last until the end of this year, that for the price of the single user license, you get all the modules plus the GPU. So this is a very, very attractive offer that we are offering until the end of next month. Now, before taking some time to answer some questions, I just want to mention that RiverFlow2D has been linked to Autodesk InfraWorks, and this is called the Project Boulder. It's in beta phase now, and it's available for free under the Autodesk Labs site, and you can download the software InfraWorks 360 and also RiverFlow2D special version for Autodesk InfraWorks. And also we have, actually next week, we have a special presentation, a class on the Project Boulder at the Autodesk University at Las Vegas. And this is a joint collaboration between Autodesk and Hydronia. You have more details on our website. Okay, so let me have get some time to answer the questions. And I have a few of them here. Let me check my time. Okay, I can handle maybe 2 or 3 now. Okay, I have a technical questions here. Okay, I have a questions about the explicit scheme. Yeah, we use a finite volume explicit scheme, but we do not use CFL greater than 1. So we do not overcome the CFL criteria. So our CFL needs to be below 1, but it's automatic. I mean, you don't need to tweak that, or I mean, it's the time step is automatically adjusted during the computation. It's not something the user may want to deal with. So it's not partially implicit. It's purely explicit. The model, okay, I have questions about how the model handles bridges and culverts. Unfortunately, I don't have time to answer this question in full, but if you go to your website, to our website, you will see a webinar there that you can watch for free, and it explains how the model integrates rivers in rivers, bridges, and culverts. Now the bridges are in 2D, are handled in 2D. As an internal boundary condition, and it's very nice feature. It's been validated with experiments and so forth. And you may want to look at that webinar that we provide there. Also, the culverts are we use the Federal Highway Administration formulation. So the model actually computes the discharge based on the culvert characteristics, and it handles tailwater effects and so forth. Okay, okay, very well. I have someone there from Autodesk in Brazil that is going to be in Autodesk University. Okay, we'll meet there next week. Great. They are working on Mariana Dam break. Oh, very good. Okay, so I have other questions here. I have a question here that is, I'm not sure I understand it well. When spatial step is large and time step is small, why does the result become different? Well, I don't know. I mean, this is Gerais results. In RiverFlow2D, results are the same regardless of the time step. But Gerais, what the developers told us is that when you have very rapid flows or very high accelerations, the numerical method they use for advancing in time has some limitations and does not converge to the right solution, or it depends a lot on the time step. And it supposedly will be fixed in the future. Do we need to have an SMS license? Well, if you get the full model, you get the SMS license with it. And actually, the price of the single user license, it has SMS. And if you have SMS already, you only need to buy the model engine that costs $2,975 US dollars. The full model price is $5,875. That includes SMS. You can go to the website and look at the prices in more detail there. How do we avoid singularity problems with dry bed? Well, that's a good question, but it goes beyond this webinar. You are welcome to look at the papers that we have published on how we deal with that issue, but this is a very accurate way to deal. We can deal with water elevations of 10 to minus 6 meters, so 1/1,000,000th of a meter. It's possible to run flow in rivers with any topography. You can use rivers with any topography, any flat variable. Okay, I have other questions here. Yeah, I think I need to stop now because I'm running out of time. Completed the hour, and I'm very glad about the attendance today. Oh, I'm sorry, I have a final question here that I want to address because we get this all the time. What's the difference between the RiverFlow2D and Flow2D Mudflow simulations and dam break? Well, the RiverFlow2D and Flow2D are two completely different models. They have nothing in, they're similar in names somehow, but they have totally different models are. Now, Flow2D has a single rheological formulation for Mudflow. RiverFlow2D has 8. One of them is similar to the ones in Flow2D, but the 7 other are different. Now, Flow2D is two-dimensional model with grid elements that are square, uniform square, with only 8 different velocity directions at one grid element. So you don't have a full two-dimensional depiction of the velocity at the grid element level. RiverFlow2D is a full 2D model, and you can adapt the mesh as much as you have seen. You can adapt the mesh very, very easily to any geometry. So I think that those are the main differences of the RiverFlow2D with Flow2D in regards to Mudflow and dam break analysis. Well, I need to let you go. I thank you so much for your listening to this webinar today. Feel free to contact me if you have further questions. We are happy that if you want to download the trial version, we provide all the files there, and you can use it for a month or so, or 15 days. And if you want to look at other webinars, go to a website and you can register to download for free other webinars as well. So again, thank you for attending, and stay in touch. Bye-bye.